We've been doing a lot of analyzing of inverse functions, thinking about how to compute them, thinking about under what conditions they exist, and we're finally getting to the main theorem. So we're going to prove our main theorem for when inverses exist and what their formulas are like. Now the proof we give here is going to be kind of informal. If you want a formal proof, the proofs included with the in-class activities will give you that, but this will at least give you the main ideas of how to prove the theorem. So remember what our theorem is that we sort of got to at the end of the last video. If you have a function f from a to b, then three things are true. F has an inverse if and only if f is both injective and surjective. Second, if f has an inverse, there's only one. The inverse of f is unique. And third, if f has an inverse, then the formula for f inverse is given in ordered pair form by BA in B cross A such that f of A equals B. So remember what that means is if you look at the ordered pairs of f and the ordered pairs of f inverse, they are reversed from each other. So if you take an ordered pair from f, you reverse that to get an ordered pair for f inverse. The inputs become outputs, the outputs become inputs. All right, well, let's start with 1. And actually, we've already proven part of 1. We proved the part of 1 where we assume f has an inverse, and we showed that f is both injective and surjective. So all we have left to prove from 1 is assume f is both injective and surjective, and then show that f has an inverse. So how do we do that? Well, first thing we're going to do is we're going to find a guess for what the inverse is. And if we're peeking at number 3, we have an idea of what that inverse should be. So I'm going to define G equal to the set of all ordered pairs BA such, that are in B cross A, the Cartesian product of B and A. And the rule for being in G is going to be that f of A is equal to B. In other words, if I have an ordered pair, I need to be able to put the y coordinate into f, and then the output B is going to be the x coordinate, right? And that's exactly what we were saying with when we were talking about reversing the coordinates for f inverse. Now, I'm calling it G because I'm not going to be so arrogant as to say, yeah, that is the inverse. I'm saying G is a function, and I'm going to prove that function is equal to an inverse. All right, so we claim that the G is an inverse of f. So we're being a little bit humble there. So we have to deal with a few issues first. The first issue is we have to show that G is a function, right? And we have to show it has the correct domain, so the domain is B, and it has to have the correct codomain, A. And just to remind you, when I say B comma A is in G, what I mean is two things, right? First of all, I need to know that B is an input of G, and then when I put that B into G, A is the output. But also, by the rule that we gave above, if we put A into F, we get B as an output. So there's two ways that we can think of that ordered pair. One, by the fact that it is part of G, and so inputs and outputs of G are determined by the x and y coordinates. And second is the rule for how that ordered pair got in there to begin with. All right, so we have three issues. It's a function, has the right codomain, has the right domain. So we'll start with the domain, right? And with the domain issue is can we take everything in the domain B and put it as an input of G? So let little b be in big B, and I want to show that little b is an appropriate input for the function. So how do we find out what its output is, right? Because in order for it to be an appropriate input, it has to be able to get us an output. Well, the nice thing about what we know about our function, what we're assuming, is that f is surjective, which means that little b is an output of our function f, which means that there's some little a in big A such that f of A is equal to B. That's exactly what surjective means. So by the definition of G, right, well, what is the definition of G? In order for an ordered pair to be in G, we need to have f of A equal to B, which is exactly what we have. So that means that BA is in G. F of the y coordinate A is equal to B, and that means it's in G. That means G of B is defined. Specifically, G of B is equal to A, right? We just found that, right? Because B is the input and A is the output. So that means big B is our domain for G. So that works out. So now let's look at the codomain. The codomain should be A, right? Because we're switching the domain and codomain for the inverse. So now if B comma A is in G, what we need to show is that that y coordinate, little a, is in big A, all right? And we can't just say it's in big A because it's the same letter, right? Same type of letter. That's not right. We got to actually show that it's literally in the set. Well, what does that mean? By the definition of G, that means f of the y coordinate has to be the x coordinate. So f of A is equal to B. But remember, that makes A an input for f, and the only inputs that are allowed for f are elements of A. So that means little a is in big A. Well, if little a is in big A, that means big A is the codomain for G, right? So when B A is in G, that means the little a, which is the output of G, is going to be in big A. So that means A is the codomain for G. All right. Now, the last of our initial issues, these aren't even all of our issues, these are just the initial ones, is we've got to show that G is a function, right? So what does that mean? Well, we already know G is a set of ordered pairs, so that's off to a good start. But we also have to be able to satisfy the consistency rule, right? So what that means is every input, you can't have an input with two different outputs. So let's do this by contradiction and pretend for a while that G is not a function. Well, if that's the case, then you're going to have one input, we'll call it B, that has two different outputs, and we'll call them A1 and A2. And when we write that in ordered pair form, that means BA1 and BA2 are both part of the function G. Well, what does that mean in function notation? Well, it means that, by the definition of G, that means that f of A1 is equal to B and f of A2 is equal to B. Those are the definitions of what it means for an ordered pair to be part of G. But since both of f of A1 and f of A2 are equal to B, that means they're equal to each other. So f of A1 is equal to f of A2. And that's an issue, right? Because we have two different inputs, A1 and A2, that go into f that give us one output for f. That contradicts the assumption that f is injective. So that means G has to be a function. All right, so we know G is a function. We know it has the right domain. We know it has the right codomain. Our second issue, and it's actually our last issue too, is G an inverse, right? Because remember, our whole purpose of this proof was proving that we actually have an inverse and that inverse is G. So we have to use the definition, which means that we have to, if we're given an element of A, if we put A into F and then put that into G, we need to get back to A, right? So the question is, what is G of F of A? We want it to be A in order for G to be an inverse. So let's see. So we don't exactly know what f of A is, but we know it's an element of B because those are where the inputs are. So I'll call f of A equal to little b to indicate that it's in B. So, well, but that equation also looks a lot like the equation for the definition of G, right? By the definition of G, if B is equal to f of A, that means BA is part of the function G. But now if we look at that as B being the input of G and A being the output of G, that means G of B is equal to A. And since we have a formula for B, B is equal to f of A, we can put that formula into G of B equals A to get G of f of A equals A. And that was the first part of what we wanted to show. Now we're not quite done, right? We've shown that G of f of A is equal to A. Now we need to show that when we do G first and then F, we get the original input as well. So if we start with little b and b, we want to ask ourselves, what happens if we take G of B, put that into F, does that take us back to B in the end? Let's see if we can do that. So we're going to play the same trick as we did in the beginning, in the first case, and we're going to let A be G of B, and we're going to play with that equation. So what does that mean? Well, in terms of G, it means B is the input and A is the output. So for G, right, so we have G of B is equal to A. That means that B is the input for G, A is the output for G, so BA is part of the function G. But remember, part of our definition of the function of G is that if we put the y coordinate into F, we get the x coordinate. So f of A equals B. So remember, that thing means two things. It means G of B equals A. It also means that f of A is equal to B. And so now what we have is, remember, we have a G of B equals A. And so if we put A equals G of B into that equation right next to it, f of A equals B, we get f of A, which is f of G of B equals B, which is exactly what we wanted to prove. All right, so that just took care of one. We got one, now we've got 2 and 3 left to do. All right. But in any case, I do want to note that what we have showed, that we show that g of f of A is equal to A for all little a and A. We've shown that f of g is equal to B, B is equal to B for all B and B, which means that g is an inverse of f. And that takes care of one. Whew. Okay, 1 down, 2 to go. All right, we're going to skip 2 actually, and we're going to prove 3. And it turns out once we prove 3, proving 2 is going to be easy. But we'll prove 3 first. So we're going to assume that f has an inverse, and we're going to show that if inverse has to equal the set of ordered pairs BA, where f of A is equal to B. All right, so to make our little lives easier, we're going to set G equal to the set BA such that f of A is equal to B. So remember, think of G as it's a set of ordered pairs. And our goal then is to prove that f inverse equals G. Right? We have f inverse, which is our inverse function, and we have G, which is defined as the set of ordered pairs BA, such that f of A is equal to B. We want to show that those are literally the same. But the same what is the real question? Well, a cheap answer is they're the same function. But the thing to remember is that f and G, the way we were defining them, they're both sets of ordered pairs. So they're equal as sets, which means that if we want to prove that they're equal, we got to go back to the stuff we did back in chapter 5. In order to prove they're equal, we have to prove it the same way we prove any two sets are equal. We have to assume that you have an ordered pair in F inverse and show that that same ordered pair is in G. And then you have to assume that you have an ordered pair in G and show that same ordered pair is in F inverse. Exactly the same stuff we did back in chapter 5. All right, so first step, assume that BA is an F inverse. What does that mean? Well, that means f inverse of B is equal to A. Duh, right? B is the input to f inverse, A is the output to f inverse of B is equal to A. Now, if we take both of those sides of those equation and plug them into the function f, here's what we get. Well, when we plug in f inverse of B into f, we get f of f inverse of B. When we plug A into f, we get f of A. So that means f of f inverse of B is equal to f of A. Now, if you look at that left-hand side of the equation, you have f and f inverse as compositions of each other. And the definition of inverse functions is they cancel each other out. So by the definition of what the inverse function means, we have f of f inverse of B is equal to B, right? They cancel each other out, which means that B is equal to f of A. But guess what? B equals f of A is exactly the test for BA being in G. So by the definition of G, that implies that BA is in G. So we assumed that BA was an F inverse. We showed that BA is in G. We're halfway there. So now we're going to do the other direction. Now we're going to assume that BA is in G, and we're going to show that BA is in F inverse. So remember, the definition of G is that if you plug the y coordinate into F, you get the x coordinate. So F of A is equal to B. Now we're going to play some more with the inverse functions. We're going to apply f inverse to both sides of this equation. Since f of A is equal to b, if we plug both of those into f inverse, we get the same output. So f inverse of f of A is equal to f inverse of b. And again, if you look at the left-hand side of the equation, that f inverse and that f are going to cancel each other out, right? So f inverse of f of A is going to equal A. And when we plug that into the equation, we get A equals f inverse of b. But now if you look at that equation, that means that B is the input for F inverse, A is the output for F inverse. So if we write that in ordered pair form, that means input B, comma, output A is an ordered pair in F inverse. So we assume that BA was in G, we showed that BA is in F inverse, and so that actually completes the proof. So put this together, we've shown that F inverse is equal to G. And remember, G is equal to the set of all BA such that f of A is equal to B. So that means we've proven 3. Right? We've proven that f inverse is the set of all BA such that f of A equals B. All right, so we've proven 1, we've proven 3. Now we're going to finally prove 2. 2 is actually going to be pretty easy, right? So we're assuming that f has an inverse. So in number 3, we've already proved that if f has an inverse, we know what the inverse is. It's the set of all b, a, and b cross a such that f of a is equal to b. Well, that's the only possibility for f inverse, right? If f has an inverse, then f inverse has to be that one function, which means that it has to be unique. So actually, when we prove 3, we prove 2 automatically. We just didn't realize it. So that completes the proof. So that's the end of the proof. Again, there are no activities for this one. So move on to chapter 7, I guess.